300 miles from land, the alarm screams through the engine room. Seawater is pouring through a cracked hull plate, flooding the compartment where the ship's massive diesel engines thunder at full power. The real crisis is hidden. Saltwater is infiltrating the freshwater cooling system, with chloride ions attacking metal from within. The chief engineer faces a decision that will determine the ship's fate. The options are brutal: keep the engines running and accept catastrophic damage, or shut down completely and drift powerless in open water. Both choices could destroy the ship, just in different ways. To understand why, you need to see what's happening inside that engine. Deep in the hull, a cathedral of steel and fire. The main diesel engine, 40 feet of forged metal, spins at 100 RPM, each revolution driving a shaft the width of a tree trunk through the ocean. But this machine generates volcanic heat. To survive, it depends on a closed-loop freshwater cooling system, pipes threading through cylinder jackets, heat exchangers, pumps cycling thousands of gallons per hour to keep metal from melting. That freshwater never touches the sea, by design. Seawater cools the heat exchangers from outside, but the two systems remain separated by steel walls. The moment saltwater breaches that barrier and enters the engine's veins, the clock starts ticking. And here's why that breach is so catastrophic. Seawater isn't just water with salt. It's a chemical weapon against metal. Every litre carries 35 grams of dissolved chloride ions, molecules that hunt electrons and tear metal atoms from their bonds. NOAA's corrosion studies reveal the brutal math. In freshwater, a steel cylinder might last 20 years. Submerge it in seawater, and that lifespan collapses to 10, a 50% reduction in longevity, measured in months of accelerated oxidation. Inside a diesel engine running at full power, this means catastrophe. Cylinder walls pit and crack. Heat exchangers perforate. Bearings seize as protective coatings dissolve. The machinery doesn't just wear, it disintegrates, one chloride ion at a time. Once that salt water crosses the threshold, the cascade begins in 3 brutal stages. First comes the heat. Cylinder temperatures spike as corroded passages choke coolant flow, metal expanding beyond tolerance, gaskets beginning to weep and fail. Then the seizure. Pistons grinding against cylinder walls as protective oil films break down. Bearings locking as chloride eats through bronze and steel. The engine shuddering as friction transforms motion into catastrophic heat. And finally, the irreversible degradation. Heat exchangers perforating, coolant mixing with lubricant, the entire system poisoned. American Bureau of Shipping data confirms it. Seawater intrusion creates damage that cannot be undone, only replaced. Which brings us back to that impossible choice. The chief engineer decides to keep the engines running. Each revolution now comes at a steep cost. Forward motion purchased with metal. The engine will survive for now, but repair costs are already mounting, one corroded bearing at a time. The numbers are staggering. Marine Insight documents that a severely corroded main engine demands over $500,000 in repairs. New cylinder liners, heat exchangers, bearings, seals. And that's if the block itself survives. Every hour the salt water circulates, the damage compounds exponentially. Another option exists: shut down the engines completely. Allow the ship to drift aimlessly, powerless at the mercy of the ocean's currents. And here's why that option is equally terrifying. The US Coast Guard's data reveals a disabled vessel can drift for days, sometimes weeks, at the mercy of wind and tide. In 2020 alone, the International Maritime Organization recorded over 3,000 engine failures at sea. While the crew works in darkness to repair what saltwater destroyed, the ship becomes a ghost, invisible to radar at close range, drifting into shipping lanes where a collision could split the hull in seconds. The chief engineer stands in the flooded compartment, contemplating 2 grim certainties: run the engines and face $500,000 in damage, or shut down and hope for rescue before drifting into a tanker's path. Which would you choose? No safe option exists. No manual can guide this moment. Only the reality that a choice must be made. Ultimately, survival isn't about evading damage. It's about accepting the right kind of damage. This nightmare isn't theoretical. It's a recurring reality documented in maritime records. The International Maritime Organization's 2020 data shows over 3,000 engine failures at sea, each forcing crews to choose between catastrophic damage and drifting into uncertainty. And Lloyd's register risk assessments confirm the calculus. Every disabled vessel becomes a collision hazard, drifting blind through shipping lanes while crews gamble on repairs. This isn't engineering theory. It's the hidden vulnerability that turns ocean crossings into calculated bets against corrosion and time. Yet here's the paradox that makes this crisis so brutal. These engines were engineered for the ocean's brutality, designed to endure decades of salt spray and storm. But that design rests on one unshakable assumption, that the freshwater barrier will hold, that the two systems will never meet. But marine insight confirms the gap between theory and reality. Every seal, every gasket, every welded joint is a potential breach point. The system isn't vulnerable because it's poorly designed. It's vulnerable because perfection is impossible when metal meets the sea. So the chief engineer makes the call: throttle up, accept the corrosion, and run for port before the ship becomes a drifting tomb. Because in the end, survival isn't about preserving the machine. It's about choosing the damage you can live with. And that's the hidden truth of ocean engineering that brings us back to that screaming alarm. Systems we assume are bulletproof fail at the seams. The question was never if the barrier would break, only what you'd sacrifice when it did.